be the thrilling finale of my 5-part lecture series. Thank you for still coming to the last talk. So I'm going to pick up where I left off last time. So let me try to remember what I was doing. I was explaining that I'm going to try to coarse grain. So I have this equation that I want to homogenize. I was muted. Okay, well maybe that was for the best anyway. So you can keep it like that. So I'm discussing how to coarse grain the coefficient field. And the idea is that as you zoom out, you want to remove the small details, I was saying. And so we want to kind of replace in every box the coefficient field by maybe a constant matrix or something like this. And we actually had two matrices. One was we called A star. So given a little box, maybe this is the box sub n, we had an A star like this, and we had an A, which was bigger. And in general, these won't be equal, and the gap between them is kind of the uncertainty and how well things have homogenized by that scale. And let's see, the nice thing is that if you break one of these boxes or any other box into smaller little boxes and look at the coarse-grained field in there, we know that this is upper bounded by them. This was subadditivity. So you sum over z in maybe some smaller scale, k. You sum over all the little boxes in this box. You put a slash in the sum to denote average. And you look at the coefficients there. And so this is upper bounded by that. And the other one is going to satisfy the sort of harmonic mean inequality. So it's going to satisfy this, like with the inverses. If the sum over the same thing here, we put inverses here. Okay, and maybe I'll actually take off the inverse, flip the inequality, and put the inverse on the outside.
The sum is a star, or is it?
It's the star.
Also.
Yes.
Not as in the first one.
Not as in the first one, yeah. So this one is the harmonic mean. So you remember that when we have a coefficient field A of x, and we want to compute the homogenized matrix A bar, we know that it's between the mean and the harmonic mean. Okay, this is the sort of only easy to prove nice inequality that you have. And this has equality if the fluxes are kind of trivial, and this has equality if the correctors are kind of trivial. If they're both trivial, then actually you had a constant matrix to begin with. And these coarsen matrices, that's right. These coarsen matrices satisfy the same sort of thing. So this upper bound one is seen by this one, and the lower bound one is seen by this kind of like sibling quantity. Okay, and if they were and we have a relation between the two, so you can put this over here and you have a kind of string. Okay, and it would be great if these were equal, because then we would know that for both of the quantities, if everything would be equal, that we would have a quantity that's crushed between its mean and its harmonic mean. And you can think, oh, the harmonic mean can be a lot smaller than the mean. But in small contrast, if these things were all about the same size and their sort of sample variance was low, actually the mean and the harmonic mean are close. And so the difference is the square of the kind of the sample standard deviation. Okay, and that allows you to kind of in a way linearize the noise and see that in effect you're dealing with a simple sort of additive thing. It's not subadditive, and this one's kind of in a way super additive, except with inverses. It's no longer just subadditive and superadditive, it's additive. And so you've sort of made something additive, which is really nice, because then you can use your independence assumption very, very easily. Okay, you don't need anything fancy for your independence assumption. You can use you have a sum of independent random variables, or if you have any other kind of mixing condition, you can say, okay, I have a sum of random variables, which are really local random variables, because these coarse-grained coefficient fields only depend on the environment really in the set that they're coarse-graining. And so you can essentially, the hard part of this problem, as I said yesterday, is that these things are very sort of nonlinear functions of the underlying coefficient field. But as you coarse grain you've actually sort of linearized and they become linear functions, and then it becomes easy. So you sort of you've made the hard part of the problem trivial. You have to squeeze these together somehow. And so the most interesting part of the problem is the squeezing together until they're small enough that then things become kind of additive and simple. Okay. So I'm going to explain how we squeeze these together. And it's, you know, in a way, it's kind of like a proof in regularity theory. So when you are trying to prove that you have some equation and your solutions are C infinity, and it's an elliptic or parabolic type equation, often you get stuck on low regularity, right? You have a weak solution without much, you know, like your solution is H1, and you just need to prove a little bit of regularity. And if you can prove a little bit of regularity, then you can use Schauder and bootstrap. And the Schauder and bootstrapping part is easy in a way. The hard part is to get a little bit of regularity. So in our approach to this problem, it's like that. If we can just squeeze these together with some sort of, you know, small exponent of a rate, then later we can bootstrap, you know, to our heart's content and make the rate sharp. Okay, so I want to explain how we get these to be close together, and then maybe if there's time, I will explain a little bit of how the sort of, you know, bootstrapping part works. Okay, are there any questions? I'm sorry, I'm going to go a little faster because I'm starting to realize that the amount of time I have is not infinite. Like it felt like in the first lecture, I had like a lot of, okay. So how does this work? Well, so let me remind you what these things are. So was the minimization problem for the Dirichlet problem. So this was the, well, let me write it like this. So if you write, so this was the matrix for the quadratic form for the thing that was the subadditive quantity. So we had minimum over W with affine boundary data of the energy of this W. And for the other one, we had, it was the inverse that was kind of defined through the quadratic form. And this was a soup over all W with no boundary data of, let's see, there's a parameter E minus, what am I doing? E dot grad W minus 1/2 the energy. Okay. So and remember that this one was kind of supposed to kind of look like a Legendre transform of that in a way, except that the soup, there's an integral in between. There's kind of an integral in the way, but it looks like a Legendre transform. And so we had an inequality that, if I write it in terms of matrices, looks like this. Let me write it with P and with the dual variables P and Q instead of writing E everywhere. Inequality like this. So we got this inequality because, so where did this come from? Well, it came from taking the minimizer in this one and plugging it in there, and then just saying that because I have a soup here, it's bigger. So we got a lower bound on this one, and the lower bound is P dot Q minus that, because this is minus the energy. And so we just rearranged it. So that was last time. And so it turns out that the difference between these matrices is controlled by kind of the lower, you know, like how close that is to being equality. Okay, so let me write that down. So it's actually, it's better in a way to write it like this. And then, okay, this thing we should just give a name. And this is not a very good name, but the one that we decided to give it is J. So so we called this J. Yeah, so I'm now that I'm in the fifth talk, I'm actually at the part of the theory that we made a contribution to. So I should say who my collaborators are, because most of the talk was about classical stuff. So the stuff, you know, we defined the A star quantity with Charlie Smart. Or maybe I won't write first names, it'll take too long. Okay. And then we did the sort of bootstrapping part of the theory with Jean-Christophe. There is a sort of rival theory that's independent of ours, that's due to Gloria and Otto, and collaborators like Stefan Neukem, Julian Fischer, Mitya Drinks, and a bunch of others. So, okay, so we have this J, and we are going to measure how close these matrices are to each other by how close J gets to 0 in the following sense. We have a bound like this. A of this minus a star of the same set is bounded by, oh yeah, sorry, can't remember. Okay, so it's bounded by JPQ, and you're supposed to, let's see, sup over P equal to 1 and inf over Q. I think I did that right. In other words, if for every unit vector P, you can find a Q that makes this thing small, then you can bound this difference. Okay? And what you discover, if because this is kind of a quadratic thing, what you realize is that if you optimize the Q given the P, the relationship should be linear. There should be a matrix for that. So let's just say that we have a matrix B so that we don't have to write the inf. So if for any B, you can write this. You could write this, and then if you were putting the B here, then you would know that the mapping P goes to BP is achieving equality here, and when you know that, then you know from convex analysis that the B is the gradient of the P or whatever. So this B should be also close to these matrices. So you can also over here write B minus this squared plus B minus the other one squared. All of this stuff is on the left-hand side, and on the right-hand side, we just have that, at least up to, there's a constant C that I didn't write, okay? Now, what's funny is that here there's a square, and here there's not a square. Yes?
Just a small question. The difference between sup and max.
Yeah.
And min.
I use them interchangeably, and I forget that I.
Okay.
Yeah.
So there's
it's a max, yeah. Yeah, there's always a. Yeah. Okay. I write it with 50% of the time I write sup, and the other 50% of the time I write max. My undergraduate analysis students are always confused about that. Okay. They never figure out what sup means because of that. I have great teaching evaluations. Anyway, these guys are closer to each other than they are to the B. Okay, so you can put like a bar here, and you'll know that these guys are kind of square root of that away from a bar, but they're close to each other more. And so what that's saying is that sort of the coarse graining is doing what it should, right? When you coarse grain, you find what the real thing is doing more precisely than if you just made them all be constant, like B. Okay, so the coarse graining is seeing more information than you would see if you just tried to put the homogenized matrix there. Okay, and so the lack of the square here is actually what makes the thing work. So it's a bit weird, or actually it's a bit normal, but this looks like a typo when you see that. You don't have to write this one because there's a triangle inequality, but the first two you have to write. Okay, so what we learned from this is that we should actually just try to control this. And this thing we call the convex duality defect. So the sort of defect in the convex dual relationship between these quantities, and we're going to try to make this thing decay. So this is essentially the same as saying we want the difference between these matrices to decay, but it's slightly more precise in what you want to decay. That, not that. Okay. Okay, so the other thing so how are we going to do this? The goal is to show that this quantity, when you go from scale n to scale n plus 1, will contract by some factor less than 1, like in a decay of oscillation estimate. Okay, so in order to do that, I'm going to introduce a tau n. Oh, yeah, I should say one more thing, which is that here I'm not, these things are all random variables at this point. All these quantities are random variables or random matrix. I mean, they're matrix valued random things. But what we should really do is keep track of the expectation. So our goal is really to estimate this and prove something like this for some matrix that we'll call A bar. I mean, we'll discover actually A bar in the iteration. So, but for some matrix, we want to prove this. The length scale, so where alpha is some positive number. Okay, so the reason is that 3 to the n is the scale. It's the size of the cube. So this is really kind of a small algebraic rate. Okay, the size of the alpha is not really important. Actually, at this stage, you want the alpha to be smaller because the thing that you're going to get out of this is a kind of large deviations like estimate. Okay, we're not going to prove a large deviations principle, but we're going to prove an estimate which is at the scale of the large deviations estimate. So, and you're more interested in the large deviations type estimate than you are in the CLT type estimate at this point of the proof. Okay, so we want to prove this. The way that we're going to prove it is to show that this thing is going to contract. So we want to prove this inequality. And this is really in the spirit of the coarse graining. It's in the spirit of what I said yesterday, which is that we don't want to, the scale, we don't want very large scales to talk to very small scales. We want every scale to talk to the next scale. This is a number less than 1. Yes.
Is it clear why the goal being just a rate and expectation is going to imply that you give an almost sure rate?
So the thing about this J is that this J is actually subadditive because everything in it is subadditive and it's non-negative. So you have a quantity that's subadditive and non-negative. So if it were converging to 0, if you have a subadditive quantity, you can control the fluctuations above the mean. You can crush them because you can just say, to be above the mean, the sum of the IID stuff would have to have a big fluctuation because the inequality goes in the right direction. So since this is going to 0 and it's subadditive, if you can control the expectation, then the fluctuations are immediately obliterated in like one line. Okay, so it's just
subadditivity.
Yeah, and that one line is where we use mainly that's the strong use of independence, if you want. So if we have this, then we'll also have a very, very strong estimate in terms of like we'll have a large deviations type bound that you get in one line, and I can explain that. Okay, so I'll explain that in a minute. There's a lot of little details that are not particularly important, but if you don't understand one part, then you get confused. So if you have a question, let me know.
Is this square missing on the first line?
Yeah, no, there's not. It's not missing. Yeah, it's not missing. So that's in fact when we wrote this in our notes with Tuomo. Now we're saying we have to say, footnote that there is not a typo. The square because it looks like it should be there, but it's not there. It's because the estimate on the difference is actually better than the gap between this and this. This is like making this you have to square root, but the other ones are closer. Yeah. Okay. And that's what you would imagine would be happening if the thing was really coarse grained. Okay, here we go.
Right, so I
because
you want to choose the B so that the right-hand side does what you want.
Yeah, the other ones are there just so that you can say, by the way, like corollary, they're also converging to the constant guy. Because we're going to put a constant guy there and see that it works. Okay. Okay. And you're going to say like, oh, corollary, they both go to A bar because they're close to each other, basically. Okay. Because you may worry that they're close to each other, but they're moving around. This is saying, no. You can control their fluctuations. Actually, you can control their variance by the J. Okay. So now what was I saying? So I want to prove this for some number less than 1, right? It's like a decay of oscillation estimate, if you want. And how are we going to do this? We're going to define this to be the difference between scale in and scale in plus 1 of these quantities. So it's like you just write this. 1 minus. So I'm not. By the way, I'm not actually going to prove this. This isn't true. This is too naive to be true. But we'll prove something that's morally that. Yes.
So in principle, there in this estimate that you want to prove the n plus 1 and theta n, you have the right to make the matrix A depend on n, right?
I could, yeah, and that's right. And I will have to do that, yeah, because you should not as we were discussing yesterday, putting A bar here would be horribly inappropriate. And so if you try to do that, your proof will be broken, and as it should be, right? So we will not put A bar here. It'll actually be A bar in, and we won't actually prove this. We'll have not just one scale, but a cascade of scales, which will be discounted as you go down. Okay, so it'll be more complicated. But at the first level of approximation, you think I'm going to prove that, okay, and you try. Anyway, okay. So anyway, what do we get here? So what do I want to define? So I want to define the difference between the quantities at the scale. And I should take expectation. I'm not doing this right. I should be taking expectation inside. And then I'm only putting absolute values because I can't remember which direction the inequality goes. But one's always bigger than the other, basically. But I just don't want to have to think about that. Okay, so I'm just looking at the difference in expectation between the two scales and saying that's tau in. So this is we call the subadditivity defect, or maybe I should call it the additivity defect. It's how subadditive are these quantities? How much is the expectation moving? And so what you find is that if you look at this J, the J actually controls that. So you can show that. Let's see, so how does this work? So this thing is actually controlled by C times the difference in the expectation of the J itself. Or maybe, yeah, so what you do is you say, I'm trying to remember how this works. Well, what am I trying to do? So yeah, so this is actually expectation in J. 1, P, and you can put anything here. So I can put a bar here. And P, A bar, P. Okay, so you put this. Now, is this going in the right direction? This one should be smaller, so no. So let me put that. Okay, so what you find is that I should put these in the correct direction. Okay, so there's no absolute value. So this gap in the additivity defect is controlled by this J thing, by the gap in the J basically. Because if you go from one scale to the next, both of these things are kind of monotone. And so the gap in the J will control the gap in each of the matrices. Okay. So what this says is that in order to prove this one, we should prove that this thing actually controls J. So we should find or we should hope that we can prove that this is bounded by C tau n. Okay, and then I'll try to explain why this is moral. Okay, so now why is this equivalent to that? Well, if you had this, you would put this here, okay, and then you would put this one back on the other side. You'd have C over here and C plus 1 over here, and then you divide by C plus 1, and you would have this thing for C over C plus 1. With the C coming from here, okay? Jean-Christophe is frowning like he's like, I'm very happy. Okay. Okay. I'm always worried that I have a typo, so I look at your face and very happy. I detected a frown. Okay. I don't understand because when everyone else gave talks, they had an easy time raising and lowering the blackboard. But when I try to do it, it's like it's 1,000 pounds. So, okay, so I want to prove this. Let me explain a little bit why that's moral. What this would say is, look, this thing's supposed to be monitoring the additivity defect. Suppose you found two scales that were, or the coefficients really didn't change between those scales. Okay, so they were both, so both of them are kind of acting like they're sort of converged. Okay, if they both act like they're kind of converged, then they can't be far apart. Okay, and that's what you want to prove. So if this thing is small, then actually the thing has converged. Because what you're worried about when you have a monotone quantity, you're worried that it's going to do this, right? You have a monotone quantity, you're simulating it on a computer, and you think, looks like the limit is this, right? But the monotone quantity can still go ha-ha and go down at some arbitrarily large scale. And this can happen in homogenization. I mean, it happens in elasticity, right? There's like some scale at which something buckles and the problem changes. And this would happen if there was somehow hidden in your problem a large length scale that appears. Okay, we don't think that should be happening, but we have to prove it. But if we know that the other quantity is like this and it's flattened, okay, we could prove that our thing is converged. I mean, here, so this would be your nightmares. They both are kind of looking like they've converged, but there's still a gap. Okay, and this would say, no, 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 that can't happen. So that's going to give you the statement. So now, how do we prove this? So what is that J there? This J is really monitoring the difference between the Dirichlet and Neumann problems with this data. Right, so the J, remember we got the J by plugging the Dirichlet problem into the Neumann energy and seeing how much it was different. And J would be 0 if they would be exactly the same. If the Dirichlet solution equals the Neumann solution with those choices of the affine data. So J, what J means is, JPQ is just the energy actually of the difference of the the minimizer of A in that cube and maximizer of the star, which is the Dirichlet and Neumann problem. Okay, so if you take the minimizer or the maximizer, you subtract them and you plug them into the quadratic form, that's actually equal to what J is for those choices. And I should say, with parameter P. This is really the problem for the quadratic form. So P dot this P, Q dot this inverse Q. Okay, so it's the problem I define those things. Okay, so the way that we're going to show that this can't be very different is as follows, is that if this tau n is small, then that means, and we're not actually going to just make one scale small, we're going to ask for a whole bunch of scales to be all small together. Okay, so we're going to say, suppose that you have a whole range of scales, tau, tau n, blah, 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 tau n plus 100 are small. So in expectation anyway, you expect that not much has happened across those scales. That means by the argument that we did yesterday, in which we had one mesoscale and one macroscale, and we compared like the solution on the big scale to the little gluing together of solutions on the small scale, we can do that here. Okay, and it means that this thing being small means that both of these guys are going to have to kind of be flat functions. They're going to have to be close to affine functions, and using the same argument that we used yesterday. Yesterday I had a mesoscale, and here I can't use a mesoscale, so I have to use something a little more precise in how I do this Poincare argument. But in principle, having a whole bunch of guys in a row that are small should mean that both of these guys are very flat. They're flat functions. Okay, so they're maybe having wiggles, but they're close to affine functions by sort of this Poincare inequality argument on a mesoscale. Except here it's going to be a multi-scale version. So I have a parameter P and a parameter Q, and as I move the P or the Q, I get solutions that are all looking flat. And you may think there has to be some redundancy there. I mean, how can an elliptic equation have two solutions which are both kind of tracking the same plane? I have two different solutions of an elliptic equation. One looks like this, and the other one looks like this. They can't actually be different, right? Because you can actually subtract them and apply Caccioppoli. And if you subtract them, you'll see their L2 norm is small. And then Caccioppoli says, at least on a smaller domain, that their energies have to be small. So very hand wavy. This is what you do. So you argue using a multi-scale version of this Poincare argument, Poincare inequality argument, that the solutions parameterized over all parameters P here of these minimizers, and the solutions parameterized by these maximizers over all Q are up to a small error parameterizing the same set of solutions. So I'll just say that the solutions of Dirichlet with affine and Neumann with affine data are essentially the same. So that's what you end up proving. Let me write down actually the inequality. Actually, I'm just trying to do that. Starting to get a bit sketchy here. I think I won't write down the very precise statement, but there's a lemma that basically controls the J by the tau. So I won't write the precise thing you get, but the imprecise thing you get is this. That if you choose this parameter correctly, you have to tune the Q to match the P so that the solutions are finding the same slope. And the thing that you should actually put there so that happens turns out to be A star, or it turns out to be the expectation, you can use either one, of the A, which is a deterministic thing, and then you put P. You can bound this essentially by the tau n. plus the variance. And the variance of the A comes up because basically the parameter that you should be using is kind of moving around a little bit. So if you want to make a deterministic one here, you have to kind of change from the one that, the random matrix that you should put here to a deterministic one. And that makes a quadratic error. And the error is an expectation is how much you'd expect. I should make this an expectation, is the variance of that quantity. Okay. So that's the first thing that you get. And this is the argument where we really see, this is the sort of key step. The other step is easier. The other step just uses this thing up here. And the fact, okay, so I have a maximum here, but this is really a quadratic function, so I can max it over like a basis or something, and that doesn't, right? And then I can change the max to a sum because it's not negative. So I can control the difference of these matrices by the max. And this allows me to control the variance of the A, because up to this error here, which is in terms of J, this thing is additive. And the variance is like the square of the fluctuations. So this thing should be like expectation of the J squared. Now I'm going to lie slightly, but okay, let's just say this. I have this. The square is on the outside of the expectation. And there's an error. There's also, I get here, what do I get? I get some, okay. So the problem is I'm simplifying the form of these inequalities so much that I no longer know what to write here. But you basically get a CLT type error, because I'm going to estimate the variance of this by going to and looking at subcubes and using additivity. So I should really be using a subscale here. Maybe that would be more precise if I wrote a K, where K is something that's much, that's less than N. And I get to choose K. And then here you would have constant 3 to the minus D over 2, because that's the number of cubes square rooted. So you get that from the CLT scaling, and you get that. So you get the number of cubes to the number of subcubes to the D, to the number of subcubes square rooted, and then 1 divided by that. Okay, so I can choose K so that this is true. And so in combination, you can iterate these. Okay, because the first line says essentially that I don't have the inequality that I want, but I have the inequality that I want plus the variance. Okay, the second line says I have the variance is bounded by the thing that I have on the left squared, but on a smaller scale. And the fact that it's squared, if you're trying to do in iteration and you have something bounded by itself squared plus an error term, the square is good, because if the thing starts small, then that square doesn't really affect the iteration. Okay, so in combination, you get J is bounded by constant J squared plus the tau n. Okay, and if the J would be small enough somewhere, then you would essentially have this inequality, and you can iterate, because the square will never hurt you. It's like a Newton iteration. Okay, so this is how it works. Again, I'm simplifying a lot exactly the details of these inequalities. It's not quite true what I'm writing here, because you have to, instead of just having one scale here and one tau n, you actually have to have sort of all the scales, but the scales are discounted with an exponential factor. So you're sort of having, in some sense, finitely many scales down, because they're sort of weighted by a decaying exponential. Okay.
Is that true about the variance? That's true about the variance testing too.
Yeah, there are more error terms that come from the fact that you're using cubes and blah blah blah. So there's some more like, error terms that don't matter. So like this term also doesn't matter, because it's you can choose K to be 3/4 in, and then this is just some small thing, and who cares? But so when you write the actual form of the lemma, there's going to this thing is not written on one line; it's written on 2 lines, and this thing, But the arguments are about what I said. The proof of this lemma is 1.5 pages, and the proof of this lemma is 1/2 page. Okay, and you see that the place where independence was used was just when I replaced this guy by the sum on the smaller cubes, and I paid this triangle inequality price. I then had to I then had to sum up the variance on the small cubes, and so I have a sum of IAD random variables. So if I have my independence assumption, I have a sum of IID random variables. Okay, so if you can make a mixing condition or whatever that allows you to sum local random variables and see that there's a contraction, and at this is the point in the proof when you would use that. Okay, so these together will iterate to give this one. Okay, and that's sort of the part of the proof where now you have a foothold on the problem. So now I can start giving the real part of my course with 11 minutes left, where, yeah. Thank you. Thank you. Jessica's on top of things. So yeah, so this is what allows you to get kind of a beachhead on the problem. And using this to grip the problem, you can prove a lot of things. So let me in the last 10 minutes explain how you would use this now to continue. Okay. I'll erase all of this. I'm sorry that that's a bit fast, but I think that's the best I can explain it in this amount of time. Part of this proof, it was 50 pages, and now it's like 7 pages. So we've done our best to make it shorter. Okay. So by the way, the estimate that you get, so to Jessica's question, I controlled this thing in expectation. So what do I get? Well, because so if I have this thing controlled in expectation, then I can use subadditivity to write this sum slash z and 3 to the n zd intersect this cube of these guys. And these guys have a small mean, so I can subtract their mean, right? Because I just estimated their mean, and I can put that inside the sum, and I can pay a price for that, for doing that, which is 3 to the minus n alpha. Okay. Now what's left in that sum I can bound really nicely, especially if I have an independence assumption, right? Or any mixing condition. So this is the place where we use the mixing condition. And if these guys were independent, you see that this is a sum of IID random variables. Even I can prove the concentration inequality for that one. You don't have to use anything fancy. It's just, you take the exponential moment argument, and you're done in 5 lines. But what does it say? It says that this thing is, okay, so I should, in order to write this down correctly, I would say the probability that this guy is greater than this plus something is going to be, or maybe I'll just, let's see, I'll write, I won't massage the estimate, and I'll just write down what is true. This thing is going to be exponential of minus, let's see, so how should I say this? Constant 3 to the minus, let's see, no, 3 to the d m, not m minus n. Okay. So by choosing the mesoscale properly, so there's an n here and there's an m here. So by choosing, if you make a smaller mesoscale, then you make this bigger, but you more brutally bound this. Okay. And if you're careful using this, so this is sort of almost at the large deviation scale, because if it would be 3 to the dm, then that would be exponential of the volume of the cube, which is the large deviation scale. This would say that the probability that the coarse grain coefficients haven't converged by that scale. So if you made this n be a finite number, so that this is just some like epsilon. So you have some threshold epsilon, and the epsilon will go down here like this or something. Then this would tell you that the probability that you make an error of order 1 is exponential of the volume. Okay. And that's the best that you can do, because that's what the large deviation that's the large deviation estimate that you should expect. This is this thing is bounded by 1/2 to the volume. And if you had the random checkerboard and you were flipping coins, this is the probability that all of the little unit squares inside of the gigantic square all came heads. Okay, you can't do better than that. And this is saying that the probability that you have an error bigger than epsilon is that. Okay. So that's what you would get. All right. If you have some other concentration inequality that tells you how these sums contract, then you'll get that instead. It's sort of, whatever you put in, you get out, because again, we sort of linearize the problem. All right, so to conclude in 5 minutes, I'll tell you how the rest of the theory works. Behind the rest of the theory is that you want to now, so you have some small exponent alpha, which is the convergence rate of this quantity. And you think that exponent alpha is not very good. How do we improve it? Well, there's a hint in how you improve it here, because in the way that I wrote these down, you see that when you have this J controlled by itself squared on the next line, plus a CLT scaling, that's going to suggest that your error is going to saturate on the CLT scaling. Okay, if you think, if it wasn't for this term, this sort of subadditivity error, if I didn't have that, and I didn't have all the other errors that I'm not writing, then these together would tell you that the alpha should be d over 2. Okay, the problem you have is that you have this pesky subadditivity error and other errors that come from the fact that you're using cubes that are just, you can't get rid of. Okay, now I think when Jean-Christophe and Tuomo and I first tried with the cubes, we got all the way to alpha equals 1, or maybe not quite 1. We got like the interval 1. So we improved everything to alpha equals 1, but because we were using cubes, we couldn't improve further. Okay, but and then later you have, if you, instead of using cubes, if you use something smoother. So the problem is that this is bad. If you think about not the cube, but the indicator function of the cube, this is bad. And you should instead find something which is kind of more smooth to partition your space. And this is good. And so instead of using a cube, you should use a heat kernel. Yes?
When you switch to those, what do you use as your boundary condition?
That's the problem. That's what took like 6 months to write the proof. Yeah. So you don't actually use the boundary conditions. You have to. So what you realize is that when you're in the linearized regime, you don't have to be so rigid in what you choose. Like, because you've driven the problem into it's basically in the perturbative case now, you can basically anything that you make here is going to work. Okay, so you have to make something which doesn't get your proof stuck, and it's just kind of technically annoying. But now we have the,
What's the idea of the right terms?
Yeah, so what you should do is you should define 2 different quantities, okay? One of which, so instead of looking at optimization problems which soup over all solutions, you should restrict radically your space of solutions. Okay, so you should only look at maybe a finite dimensional space of solutions, maybe just the correctors, okay? And the problem when you do that is that it's no longer local. The quantity is not local, because if you just look at the correctors, say defined in all of space, we said that was a bad idea. But in particular, it means your thing is not local. You can't do these IID arguments so easily, okay? So you have to define, but if you just look at the correctors, then when you put the heat kernel here and you move it around, it's going to be additive. So it'll be kind of exactly additive, but not local. Our quantities were nice because they were kind of sub-additive or whatever, but also very local. When you do this, you have to sort of give one up. So you make one quantity which is obviously additive but non-local, and you make a different quantity which is obviously local but non-additive, okay? And then you show that they're almost the same, okay? And the reason that they're almost the same is because the optimization problem is really optimizing over the same set of solutions, kind of like this argument up here, okay? But the way that you do that, the way that you show that it's the same set of solutions, is you have to show that you have to prove a regularity result, okay? If you have a harmonic function, you can approximate it really well by polynomials, okay? So if you want to use polynomials of degree 1000, you can approximate any harmonic function in a ball by a polynomial of degree 1000 in the half ball, and your approximation will be very good, okay? So in that sense, the regularity of harmonic functions kind of finite dimensionalizes the solution space up to some error. So you have to actually prove that that's true in this problem. Now that's weird because when you zoom out on a disordered elliptic equation, you shouldn't have regularity, you would think. So you have to actually prove that no, this thing does have regularity. And that's sort of the part of the proof that I usually emphasize, but for some reason in this mini course, I don't mention it until I'm 1 minute to go in the last lecture. But what happens is that this puts you into the perturbative regime, the thing I explained today. When you're in the perturbative regime, you automatically get large scale regularity. You get that on large scales, the thing basically has almost like analytic type regularity, or at least C infinity regularity. And using that, you can make the heat kernel idea work by kind of having your cake and eat it too.
And large scale regularity, you mean regularity on this polynomial approximation?
Yeah, but you have to replace the polynomials by wiggly polynomials. So you have to, like, instead of using affines, you have to use the correctors. So you have to, but yes, but essentially yes. And how do you prove the large scale regularity? What is the idea? This idea goes back to Fenghua Lin and Marco Avellaneda in 1987 in the periodic case, and they have a compactness proof. Okay, so you can imagine that we don't want to use the compactness proof in the random case, or even the periodic case, but especially the random case. So instead, we argue like you do in Schauder estimates. So I said that the ergodic theorem is a blow down version of Lebesgue differentiation. What we do is a blow down version of Schauder. So you show that because you've homogenized with an algebraic rate, instead of freezing the coefficients like you do in Schauder and using a Laplacian approximation, here you use the homogenized coefficients on large scales, and that also gives you an approximation. So on large scales, it's kind of close to being harmonic, and it's close enough to being harmonic that this regularity kicks in and then allows this to accelerate. And that's the proof. So if I had another 4 lectures, I could explain that. But that took a long time to write down, but now we have the proof compacted. So we wrote a book with Tuomo and Jean-Christophe that's like this, that has the proof. And now we can make the proof more like, okay, well, again, thank you for listening to me. I was feeling a bit bad yesterday because all these young people were giving 10-minute talks and they were stressed to finish. And I have 250 minutes. So I feel like it, but anyway, thanks for your patience, and I appreciate it.
No matter how many minutes you have, you'll still be stressed to finish at some point. Right?
Yes. Yeah, you tell jokes and you take up the time, and then you realize you have to.
Yeah, so there's a universal theorem that the stress to finish is independent of the length of the talks. But yeah, are there any other questions for Scott on his course?
Yeah, so I remember you were saying like mostly what you like to do is finite range, and you said this result is very general. Is it really that like you have something that's like almost arbitrarily bad, and then you get it up to this kind of mesoscale, and where it's like smoothed out, and then from then on you can get really good estimates? Is that? I know it's a very, very general question.
Yeah, so I'm trying to figure out what exactly you mean. So you mean?
I guess I mean.
Are you asking like what mixing condition can we do? Or are you asking?
I guess I mean like, okay, if you assume finite range, then you get very strong mixing properties, and you're good to go. And I'm wondering that if you start in kind of a worst case, does getting up to this mesoscale kind of put you into a situation where you can?
So this proof with the algebraic rate works with a very weak mixing.
Right.
Because you're just trying to prove an algebraic rate. If you want to prove the sharp rate, then you have to ask what is sharp for my assumption.
Right. Okay.
And this will given any assumption, this will output the sharp rate.
Okay.
We can almost prove a theorem that's kind of a meta theorem.
Right.
But yeah, nobody can. I mean, So the last time I was at a conference, one of the speakers said that well, anyway, yeah, it's true that, so we write it for a finite range, but I insist that we now have it formalized so that it covers all of the standard mixing conditions that are the other ones that are commonly used, and we're sharper in the integrability. So they give these examples of, these are the real examples that you want in science, and the finite range dependent case is some mathematical curiosity. And if your theory is limited to that, it's not good. And then they show a book of all the examples in science. And on those examples, our thing does better. So it really does get the sharpest result. Because there's two kinds of errors. There's the thing that goes here, which is what I've been talking about. And here you want, if it's going to be optimal, what you would really want is something like md/2, right? But then that would shrink this. And so you kind of want to be optimal in both at the same time, and allow, if you make this threshold weaker, to have this stronger. Okay, and so the thing we have does that basically for any assumption. So the way it works is you get, if you want to think about it as an induction in the scales, at some scale you make this small enough, and at that scale you're really in the perturbative regime, and then in that scale you have a different proof. It's kind of like when you're proving convergence to equilibrium for a nonlinear equation, you do you have some entropy that gets you into a perturbative regime, and then you linearize and use a different argument to actually get the conversions. Yeah, so it's like that.
Any other questions for Scott? I have a silly philosophical
Uh-huh.
question. So, okay, so it's clear that, if you have like 3 scales, you can do something as long as they're well separated, right?
Mhm.
I mean, you just have to do some work or whatever, and say in the n scales, sure, as long as they're well separated. How many scales until it stops working? Like how close can they be separated before the arguments actually stop working? And the interaction between the scales become such that you don't know how to do it anymore.
You're trying to cause trouble. You're asking me about ongoing work that I'm not ready to.
Okay.
No,
I will
I know what you're
really
doing.
await
Yeah.
the answer.
You have to wait for the answer. So the question is, what happens if you have not just 2 scales, but many scales? And if you have many scales, they can't all be well separated, right? So can you make a homogenization cascade? Yeah. So to do that, you would need to do better than we're doing in terms of the dependence, not on the scale, but in the ellipticity. So the question is, as a function of ellipticity, at what scale do you enter the perturbative regime? That's a good question. I don't know.
I guess we'll find out.
Yeah.
All right. Cool. So there's no further questions. Let's thank Scott for the great course.